So we're going to continue the discussion of unusual supernovae, and what I want to discuss is certainly relevant to the ultraluminous class, but it turns out that they can produce a very wide variety of phenomena. And what I'm going to discuss is things the pair instability can cause, thermonuclear supernovae. Basically, there are two ways a star can die generically. Adam Burroughs talked about this one the other day. A star can go through 6 metamorphic stages of nuclear burning, where it eventually arises to the point where it tries to burn iron and fails and collapses, perhaps with rotation in magnetic fields, and a miracle occurs, and the star blows up. And these are the stars that we see as supernovae. They're the stars, the massive ones anyway, responsible for making the heavy elements. But there's another mechanism, and you can actually do it on your laptop, and everybody agrees on the answer, and you get the same answer every time. So the issue is not the physics of the explosion, which I am going to explain to you, though, but whether you ever make these stars, and it seems unavoidable that you do sometime. The evolution of the massive star gets interrupted shortly after carbon burning when it reaches a temperature of about 1.5 billion degrees and starts to make a lot of electron-positron pairs. Creating the rest mass of those pairs takes energy that might have contributed to the pressure but doesn't, and so the adiabatic index goes below 4/3. The star begins to collapse, but it collapses with unburned oxygen and other fuels. It begins to burn it, and if the pulse is strong enough, if it goes deep enough, it burns enough to explode the star in one try, and we call that a pair-instability supernova. But frequently, as we'll be discussing, there might not be enough energy released on that first or second or third try, and the star pulses for a while and goes down another route. Now, this is an affliction that only affects the most massive stars. You need to have high entropy. You need to have low density at a given temperature so that the pairs play a major role in the equation of state. And so it turns out that what you need for this to happen is a helium core of at least 35 solar masses. That's not so big, but today with solar metallicity stars and mass loss rates that people like to use, you don't get helium cores bigger than 20 solar masses. Well, those mass loss rates could be off. But you can also turn down the metallicity just a bit. A factor of 2 or 3 will do, and you're bound then to encroach on this domain of pair instability. Now, see. All right, it does work. The helium core masses that you need correspond to a range of main sequence masses, and the ordinary supernovae are bounded on the upper end by about 75 solar masses, of which probably only the first 20 solar masses blow up and the rest become black holes. Atom has a hard time, and others do blowing up even the first 20. And then there's an equal mass range from 32 to 62 in helium core mass, 75 to 140 in main sequence mass, where you encounter the pulsational pair instability, which I just described, and that's going to be the main thrust of the talk today. And you go on up a little bit higher, and the instability is so violent it explodes the star, and nothing is left behind. No black hole is produced, so here's a large range of masses where no black holes will be made. And then above 133 solar masses of helium, 260 solar masses on the main sequence, all you make is black holes. And you do that all the way up to supermassive stars and maybe make the seeds of galactic black holes that way. But there are large mass ranges which would be well populated except for mass loss and the saltpeter initial mass function, where the explosion mechanism is quite well understood. Now, I'm not going to spend a long time on the pair instability itself because pair instability supernovae, because those are well documented in the literature. There's a good summary plot here that gives the explosion energy in units of 10 to the 51 ergs, and the nickel mass that's produced, the dashed line, in solar masses, and for the very upper end you can get around 50 solar masses of nickel, and you can get up to 10 to the 53 ergs of energy. So people are fond of those for powering superluminous supernovae, but they are the exceptional case. Most of the pair instability supernovae would be down here, where the IMF makes more of them, where mass loss doesn't kill more of them. But in extreme cases, you can get ultraluminous supernovae from radioactivity or from kinetic energy. And so if you just have bare helium cores, the whole light curve is due to radioactivity. And here are some results for helium cores of different masses, ranging from 70 to 130 solar masses. So this one almost made a black hole, but exploded and made about 50 solar masses of nickel, so it was very bright. Long time scales, though, hundreds of days, and none of these plots ever get much above 10 to the 44 ergs per second. That's an upper bound for the pair-instability. If you put that same explosion inside of a red supergiant, the 10 to the 53 ergs comes into play, and a fair fraction, maybe 1% or so of that gets converted into light, and you still get enduring light curves of about 10 to the 44 ergs per second for hundreds of days. If the star is a compact blue supergiant, then they look like 87A, except the time scale is long and the peak luminosity is above 10 to the 43 ergs per second. So you can get a great diversity from the pair-instability supernova. You can get ultraluminous cases, but the common cases, which might not be so easy to recognize, should be the ones that are the lower curves here. The most frequent explosions will be the ones with the smaller nickel mass, the smaller kinetic energy, making these fainter light curves, including some very faint events that never get above 10 to the 42 ergs per second. Well, that's all I want to say about the pair-instability, because I want to talk about pulsational pair. I think there's a lot of confusion about it. There's no really standard discussion of it in the literature. I hope to remedy that, and other people are working on it. But I have to give you a little tutorial, I think, about how the pulsational pair-instability works. And we start with a thought experiment. We have a 40 solar mass core of helium and heavy elements, which you just make and let it contract and don't have any nuclear burning, and its central temperature will rise as it contracts and goes through its Kelvin-Helmholtz stage. And its binding energy, starting at 0, will get more and more negative as it gets more and more bound. And then when the temperature has risen just a little bit above this, it'll become unstable. It'll go into dynamic implosion, and it'll do some nuclear burning. And the burning will release energy that raises the net binding energy of the star. And so it expands and goes back over and rejoins the blue line with a new binding energy and experiences a new Kelvin-Helmholtz evolution phase. So if it's a little explosion, it goes blip, around, and it can do that hundreds of times, in fact, just weak pulsational pair instability. If it's a violent pulse, it can go up here and go way over here and take tens of years to resume activity again. And the upper bound for how long the pulsational pair activity can go on is actually the energy required to disrupt the whole star and the whole Kelvin-Helmholtz time scale, 10,000 years. Pulsational pair activity in the models as well continues from onset to final core collapse in the end for 10 to 20,000 years. It's not something that just goes on for days or years, but it can also go on for an hour. It has an enormous range of time scales, an enormous range of energies. So here is a 50 solar mass helium core. The main sequence mass, you can multiply the helium core by 2 and add 10 and get the main sequence mass. So that's about 110 solar masses on the main sequence. And here are the pulses. The temperature goes up, there's an explosion, it expands, temperature goes down, and each blip, like on a cardiogram, is a pulse for the star. So these are, about a half dozen violent pulses during the last several months of the star's life. And the reason I show this is here's the central entropy. And during the cooling phases, during the neutrino emission in between pulses, the entropy goes down. So in the end, the instability goes away and the star becomes stable. And then it completes its life. Unlike an ordinary pair-instability supernova that blows up and leaves nothing, these stars go ahead and finish oxygen, silicon burning. They make an iron core, and it's a dang big one, is one thing I have to tell you about in a minute. It's not easy to blow up what these things leave behind. So here is the cardiogram for several masses from 38 to 52 solar masses measured in terms of the helium core mass. And in the first plot, the total duration is less than an hour. And this injects just a tiny bit of energy down at the bottom of the envelope, which might barely unbind the envelope. And you go up in mass, the pulses get longer in duration, more violent, and there's fewer of them. And you keep on going up, and the time scale gets to be weeks, and then years, and then even centuries eventually. And each pulse ejects a shell of matter when you have the few pulses. When you have many pulses, they all pile up and just eject the hydrogen envelope. So you get a range of time scales going all the way from 1 hour to a few times 10 to the 11th seconds for the duration of the instability, with the duration being a function of the mass of the helium core. The bigger cores pulse for longer, have more violent pulses. And you put these helium cores, either blow them up singularly or put them inside of red giant envelopes, you get a whole range of transients. You can get very faint single pulse events. I'll show you some light curves. You can get normal looking super supernovae, you can get ultraluminous supernovae, and you can also get a new class of sources that hadn't been discussed, where it's a very bright radio or X-ray source, but not necessarily a bright supernova, where the collisions go on out at 10 to the 17th centimeters and beyond. The energies that you get in the pulse range from 10 to the 47 ergs to a maximum of 4 times 10 to the 51 ergs. And that's one take-home message. All of the energy that you can get out of all of the pulses never exceeds 4 times 10 to the 51 ergs. So if your supernova, your light, has 10 to the 52 ergs in it, it isn't just the pulses. Something else has to add to it. That's all the model can do. But on the light end, you have many small pulses that make subluminous supernovae. Then there's a range where you make normal supernovae with an energy of about 10 to the 51 ergs. Then a range where the pulses might be years and centuries in between, where you make ultraluminous supernovae and radio transients. And then finally, a place where the pair-instability blows up the star on one try. Okay? So there's a very wide range of things that can happen. Now, the cores that are left in the end, I said it goes ahead and evolves through silicon burning in the end and makes iron cores, and they are typically 2.5, but up to 3.5 solar masses. The silicon core, the base of the oxygen shell, is the green points. These are typically down around 2 solar masses or less in ordinary massive stars, but they're out at 6, 7, and 8 in these stars. These stars are going to be very hard to blow up. Now, we'd like to, for reasons I get to later. Assassin would love for one of these to blow up, okay? But here's an ordinary supernova core collapse, the dashed line. Here's the density in one of these big pulsational pair guys, and it falls off very slowly. Here's the edge of the iron core versus the ordinary edge. The velocity, when the density is 7.5 times 10 to the 9th, is already much greater. The compactness parameter, if you follow such things, is 1 for these stars. There is no way neutrinos are going to blow up this star. But maybe rotation can, who knows? No one has tried with this massive star yet. No model builders have attempted something like this yet. But I have calculated the rotation rate, the maximum mass neutron star. This will lose 0.5 solar masses, settling down to a cold neutron star. That's a stable neutron star, and the rotation rate would be 2 milliseconds. That's with magnetic torques included. Without magnetic torques, or stretch the physics a bit, you might get 1 millisecond. But this object is going to accrete at a solar mass a second while it's trying to contract down, cool off, radiate away its binding energy and become a pulsar, and it may never get there. So today, we're assuming these all make black holes, okay? But hold out the possibility that it might make something really exotic at the end, which would have dramatic superluminous consequences, I'll tell you. Okay, the remnant masses after the pulses are over, all the way from 80 to 160 solar masses, there is a maximum of 52 solar masses. And that's one take-home message for the gravitational radiation people. There is a hole in the hole distribution. From 52 to 133 solar masses, no black holes. Prediction, falsify it. Now, you might find a way around here. Do it. If you had a triple and you put 2 black holes and added a third, all right. And if a 70 solar mass black hole evolved its whole life and never lost a gram, all right. But, you know, it's my prediction. I'm making it today. It's 52. Okay. But no bigger than 70.
At solar metallism? Or no?
No matter.
No matter.
No matter. Okay, so here's some light curves. Another prediction today. People who do transient surveys, this is not all about ultraluminous. There's 10 to the 40, I have to read it for you, 42 ergs per second. So this just touches for less than a day at being as bright as a type 2P. This is blue, 10 to 20,000 Kelvin. It's type 1. It never gets up to 10 to the 42 ergs per second. It's the most frequent kind of pulsational pair instability in a bare helium core. Might be out there. Fast, faint blue transients. In a minute, I'll show you long, slow red transients. Same thing, but with a hydrogen envelope. You add more mass, you get fewer pulses with more energy, you start to see structure, and now it's pushing up to a few times 10 to the 42 ergs per second. Then 10 to the 43, and then, do I get to 40? No, just 43. The maximum is just a few times 10 to the 43 in these bare helium cores. But highly structured things, if you see these, you know what you've seen, I think. And I don't know if you've seen them or not, but they need to happen. Again, this is not the tooth fairy blowing it up. If you ever make a helium core of 48 solar masses, that's what it does. Okay? Go look for them. And so a summary for type 1, there's a variety of transients happening. Typically 20 to 100 days, maximum luminosity a few times 10 to the 43 for type 1 for pulsational pair. So if Assassin's type 1 is not any pulsational pair, without some other big energy input, we'll come to that. But maximum of the unadulterated pulsational pair model, a few times 10 to the 43. Maximum radiated energy, only half of the total pulsation energy can be radiated. It's never going to run into a mass much bigger than itself, and that gives you efficiency of a half. And so 1 to 2 times 10 to the 51 ergs of light. Total ejected mass, typically less than 10 solar masses. Probably leave a population of 35 to 45. So not only is there a hole from 52 to 133, there's a pileup between 35 and 52. Okay, put a little envelope on this. Put a big envelope on this. Put a red supergiant envelope on the same sort of thing. These were full star models. I didn't add envelopes to helium cores, but it's sort of like doing that. Now, the mass of the hydrogen envelope is going to vary with the mass loss rate that you take, which is going to vary with the metallicity that you take. It's not going to affect what goes on in the core, but it's going to affect the light curve a lot, whether you've got 5 solar masses of hydrogen or 80 solar masses of hydrogen that you're expelling. So 70 solar mass star, it kicks the envelope off, and this is 10 to the 8th seconds here, so 3 years at 10 to the 40, a few times 10 to the 40 ergs. It's a supernova. And it's red, 3,000 Kelvin. It's very low velocity, 100 kilometers per second or so. Quite faint, hard to find. You go on up to 80 solar masses. Well, same thing, only broader and brighter. And it may last, 200 days and look like a subluminous type 2P. And you might have seen these. Go on up a few more solar masses, then it looks very much like a 2P. It has a luminosity of a couple times 10 to the 42 and lasts for 100-something days, but no radioactive tail, because all the radioactivity is going in the hole. Go on up, now you start to see something interesting. 100 solar masses, structured long type 2P. So what's happening is additional pulses are happening while the plateau is in progress. And so you're getting peaks from shell collisions inside the photosphere of the type 2P supernova that's in progress. Ought to exist. Go on up, now it gets really interesting because now the pulses, the interval between pulses is getting longer than the duration of the supernova. And so you can have multiple supernovae. And so you can have a supernova and then, a few years later, another supernova. And the ejecta of the second supernova run into the ejecta of the first supernova, colliding shells, and they can make something quite bright and quite complicated. So you have first something that looks a little like a type 2P supernova, and then a couple or 3 years later, the shells run into each other. These spikes are due to numerical artifacts in 1D simulation. Same effect Dan Kaysen was talking about. When fast-moving stuff runs into slow-moving stuff, it piles up in a thin shell. And when thin shells collide, you can get an arbitrarily high luminosity. In 2D, these would get spread out, and what I showed you there would be smoother. But we're already starting to see something, hundreds of days long with luminosities 10 to the 43 ergs per second. Going up a little more in mass. Here's the brightest optical one that I've done. The code crashed here, unfortunately, because the thin shells gave it such a fit. But it would have had at least 3 pulses going up to a few times 10 to the 43 ergs per second per pulse, and lasting of order 400 days. If you've seen one of these, you ought to know. Okay, so faint, long red transients, common, 10 to the 40, 42 ergs per second. Luminosities up to a few times 10 to the 43, but not more than 10 to the 44 ergs per second, possible from just colliding the shells. Total energy, kinetic plus light, around 2 to 3 times 10 to the 51 ergs. Preceded, in some cases, the ultraluminous ones are, by an ordinary supernova a few years before the bright supernova. That's something to look for. highly structured light curves. The number of peaks in the light curve can be more than the number of pulses because, well, the envelope comes off, there's no pulses, no shell collisions there, it just makes the first supernova. Then the next shell comes off, that's collision number 1, and then the next shell comes off, and it hits 2, but 2 plus 3 hits 1. And so you add it all up, and it goes roughly as n squared over 2 for the number of peaks in the light curve. Now, when you have intervals like a year or so between pulses, then there can only be at most 4 pulses. So n is less than 4 here. The longer events, the collisions can collide out at 10 to the 17 plus centimeters. That's more like a dense circumstellar medium than a cellular collision. And so you could see bright X-ray and radio sources after a supernova from shell collisions that weren't accompanied by a lot of optical emission. So in the drifting times, I want to say, in the remaining time, I want to say the interesting stuff. Because people sometimes say maybe Eta Carina was a pulsational pair-instability supernova. It could have been. I thought 2 days ago it was, and 2 days from now I probably will again. And here's the good stuff. You know, it's been going on for a couple of centuries. And you can have pulsational pair-instability supernovae that eject, you know, whatever is left of the hydrogen envelope. This could have been 15, but in this case it was 24 solar masses of hydrogen at 1,300 kilometers per second, and then later 7 solar masses of helium at 4,000. Very nitrogen-rich material. The remaining core, now this is the thing about pulsational pair that's so fascinating. They can make all these shells and collisions and bright stuff, and the star is still there, right? Because it can be there up to 20,000 years after the explosion, before the core finally collapses. Now, in the ones that would make Eta Carina, it's more like 1,000 or a few centuries, but a prediction would be that the star that is there now is like a Wolf-Rayet star, but it's not shining by nuclear fusion. It's just Kelvin-Helmholtz contracting on its way to being a black hole and making an ultraluminous X-ray source. There's a prediction for you, but I won't be around to see it. Okay, Eta Carina, the problem, I talked with Nathan Smith about this some, the problem is that it's maybe too much energy. It's hard to get these parameters without having 10 to the 51 ergs of energy and not 10 to the 50, as seems to be preferred. Maybe we can get around that. There should have been a brighter supernova during the Great Eruption. It should have looked more type 2P-ish than just envelope coming off over 10, 20 years. But many similarities, tweaking the model might make it work, but if it doesn't, so what? This has to happen. And so there are other supernovae somewhere else in this universe that are doing this, and you might find them. Gravitational radiation, just a one quick slide. You can't make the gravitational radiation that was seen, I claim, from any single star because everything in the mass range 35 to 133 solar masses either blows up or pulses until it has too small a mass to make the merging stars. There's great trouble getting the gamma ray burst signal out of a single star with the half-second delay that was observed. And short, I don't believe the gamma ray burst. Assassin in the waning seconds, as is appropriate. 10 to the 52 ergs of light is tough. It can be done, as Dan said, barely with a magnetar pulling out all the stops. It cannot be done by colliding shells in just the pulsational pair model. But now let's make a pretend. Let's say that core blows up because it's rotating fast. Let's say it makes a magnetar. Let's say it makes, this is what Robert was saying a while ago too. Suppose you had a 2 times 10 to the 52 erg explosion and all of these shells sitting out there and you ran into it with all that energy, well, all hell will break loose. And it does, and it did when I ran it. But what I was able to show is that you could not do it with any type 1 object. That is, the collision between the helium shells. There wasn't enough mass in the helium shells. You know, 4 or 5 solar masses wasn't enough to convert the 2 times 10 to the 52 ergs in the 40 solar masses that was expanding into light. And it just didn't work. But if I had a hydrogen envelope, I could make it almost work. And so this is 10 to the 45 ergs per second, and this is 200 and something days. This is 10 to the 44 ergs per second. So this is a super energetic supernova inside of a pulsational pair-instability supernova, starting with 115 solar masses. It'll get published by somebody somewhere. Okay. All right, concluding, you get a great diversity of events, little ones, big ones, faint ones, long ones, red and blue ones, durations up to 10,000 years. Maximum energy, 2 times 10 to the 51 ergs in light, probably. Never saw anything over 10 to the 44 ergs per second unless we did the magic thing at the end. They make black holes in a certain mass range and don't make black holes in a certain mass range. The typical very energetic ones have 2 to 4 pulses. Eta Carina might be a zombie star that is not shining by nuclear reactions. Novel prediction, if not a wrong one. It needs to have a total energy of 10 to the 51 ergs, not 10 to the 50 ergs. Needs to have had a bright supernova sometime along the way, not real bright, 2 months at above 10 to the 42 ergs per second. Nathan can say whether that's possible or not. Assassin might be the explosion of a type 2. How does the hydrogen hide? That was the point of my question a while ago. If you've got 10 to the 45 ergs per second, Avi, you were asking the other day about with the super Eddington luminosity, if you might accelerate the shells. That becomes a major effect when you got 10 to the 45 ergs per second for 30 days. And in fact, it lessens the efficiency of the shell collision because the radiative precursor accelerates the matter ahead of the shock, and so the collision is not as strong, and that keeps it from being quite so violent. But the Strömgren sphere for something that bright must be enormous. And so the hydrogen ought to be ionized to a large distance, and maybe it's not type 1, is what I'm saying. I didn't talk about the nucleosynthesis. I don't have time. It's novel because you only eject the helium and the carbon and the oxygen, a trace of neon and magnesium, no iron at all. And if these were the first stars, they would have left a definite nucleosynthetic signature on the first stars. Namely, they would look like the ultra-iron poor stars. Thank you.
That was a lot of fun. So I'm trying to think of, so you can predict lots and lots and lots of different kinds of transients, which may be mixed in among all of the transients we're seeing. And so I'm trying to think of other ways that you can help give us more information to try and keep it all straight. And one of them is that these things should be going off in like massive young clusters. But maybe there are other things like there's also, in several cases, you said the lack of a radioactive decay tail. But then maybe other hints about keeping track of the expansion velocities and combining those with the light curves to sort of sort those out from the normal core collapse supernovae.
Yeah, good point. I'm sure there'll be a lot of follow-up work, probably by a lot of other people too. The velocities are typically 2,000 kilometers per second for the hydrogen and 4,000 for the helium and heavier elements. Of course, at the edge it can move faster, but that's the average velocities I typically see.
I guess I have one other question then. So at late times, if these things have gone off in the Milky Way in the past, if we can look at the sort of the remnant that's left over, are there nucleosynthetic signatures that really stand out at all from the oxygen?
Well, if you could get to it quickly, you might still see the star there. Unless the core blows up, they will only make very light elements: carbon, oxygen, neon, magnesium, some silicon, but no iron group.
Stan?
Where?
Right here.
Yeah.
A general question. All of your models, the ones that you presented, are single star models.
Yes.
And we heard before that binaries make a big difference, especially for the eruptions.
Right.
How would you expect the predictions to change?
The key is the helium core. Whether you've had a binary or not have a binary, when the thing finally blows up, it has one helium core. And the mass of the helium core determines the physics of the explosion, the energy, the number of pulses, the duration, and so on. What you see, I mean, Schramm used to call this the weather on the star, is what the envelope, how massive the envelope is and what its radius are going to determine the light curve, the spectra, and what it looks like. And so, yes, the binary membership has to be considered. But the energetics can be considered without worrying about the origin.
Yeah, Stan, this is by far the best talk of the whole meeting. And what I like is you're not accounting for the features of things we've seen, but you're telling us things we might see.
The last meeting we were at, and I'm glad you're here because I thought you weren't here. You said, Woosley, why don't you ever make any predictions? Do you remember that, Bob?
Apparently you remember it better than me. But you're kind of promising us a lot here, and I was wondering if, Wes, just a minute. So I was wondering if you would say a little bit about the rate at which we would see these things. If there are so many, if you're going to try to explain so many things, they may turn out to be very rare things.
Yes, well, they are, because the IMF is the IMF, and the number of very massive things is small, but also there may not be any of them, or very few in our galaxy.
Well,
you have to go to low metallicity. Our galaxy is not the only place. But you go to low metallicity, and like I said, anytime you get helium cores of this, it's going to happen. All right?
Well, hats off, except I'm not wearing a hat.
All right.
Please stand. Hi. I was just wondering, following up on Nathan's question, you mentioned that if we look quickly enough, we can see the star that's left over after the pulsations, and you said it would be a hell of a large...
Most common case, it would be a Wolf-Rayet star shining at nearly the Eddington luminosity, and I'm glad you asked that. In the Eta Carina case, it would be 10 to the 40 ergs per second, which is what's inferred for the star in Eta Carina. And it's shining chiefly just because it's in this Kelvin-Helmholtz stage, and you can't tell the difference between that and an ordinary Wolf-Rayet star. You don't know what the energy source is. But there's also fallback. And it's a bit of an important computational challenge what you take for the opacity in the material that falls back, because that gives you the Eddington accretion rate. But the contribution to the luminosity from fallback could be appreciable. So it's a very bright thing, 10 to the 40 ergs per second, roughly.
And 20,000-year lifetime at max?
At the very most.
So small window to
That's the most massive, which are the rarest events. Usually, the star dies with the supernova, and then there's a range, of just a few solar masses in helium mass, where the star lives a lot longer than the supernova does.
What kind of metallicities are these things going to happen?
A third solar and less. But, who knows the mass loss rates, right? They could happen in solar metallicity. But, for the mass loss rate in the very old code, it's a third solar.
Sorry, Mr. Mancio.
So Stan, I think I might have found your long, slow red transients. This is with the Spitzer Space Telescope with my Spirit survey.
Sorry, where are you coming from?
Okay, let me stand up. I'm not that tall. So I might have found your long, slow red transients because I'm finding...
They're not the luminous red novae.
No, not the luminous red novae. These are brand new infrared-only transients from the Spitzer Space Telescope with my Spirit. Per second? We don't have spectra to confirm that, but they evolve on hundreds of days and with temperatures of 1,000 to 2,000 Kelvin.
I got through.
And they are always in grand spiral arms and spiral arms of galaxies, so regions of high star formation. But there's one problem. And I don't know if you have a way around this, which is that the progenitors are not bright blue things. The progenitors down to deep HST limits are also very red.
They would be. They're red supergiants.
So it's okay if you don't see the progenitors at all?
The fast, faint blue things were helium cores. The long, faint red things were the explosions of red supergiants that just barely got their envelopes kicked off. And to be fair, there are other ways to just barely kick the envelope off of a red supergiant. So it would not be a singular diagnostic. Elizabeth Lovegrove will talk about something else that does this tomorrow morning.
So if you want to see some of these discoveries, I will advertise that I'm giving the colloquium at 4 p.m. on Thursday at Harvard on this topic. So.
Thank you.